In the heart of war, when mud swallowed hope and fire ruled the sky, a simple curve of steel became the shelter of survival. From the trenches of France to the burning fields of Europe, the Nissen hut rose, born from one man's vision to give warmth where there was none. Years later, across the ocean, its brother was born, the Quonset hut, strong, fast, and ready to follow the soldiers to every corner of the world. Under its arch slept the wounded, the brave, and the forgotten. Within its walls, laughter returned to the sound of rain, and letters from home were read by flickering light. When the guns fell silent, these curved homes of steel remained, turning into schools, workshops, and dreams. What began as a shelter for war became a symbol of endurance for peace. The world moved on, but their shadows still stand, silent yet proud, reminding us that even in destruction, humanity can build something that lasts forever. Welcome to Britain at war. When Lieutenant Colonel Peter Nissen first trudged through the mud-soaked, shell-pocked construction sites of the Western Front in early 1916, he confronted the grim reality of a war that consumed everything in its path: lives, resources, and conventional methods of survival. Soldiers shivered in collapsing canvas tents, wooden shelters failed under the weight of relentless snow, and makeshift lean-tos offered only minimal protection from freezing rains and artillery shelling. Timber was scarce, skilled carpenters and masons were entrenched at the front, and traditional building methods, relying on posts, beams, and trusses, had become all but impossible to implement. Nissen, a Canadian-born mining engineer serving with the Royal Engineers, observed a resource lying neglected yet abundant: corrugated iron sheets scattered near supply depots, left unused because nobody had conceived how to utilize them effectively for shelter. Their ribbed, resilient surface was perfect for shedding water and resisting minor shell fragments, yet the opportunity remained untapped while soldiers froze and suffered. Nissen's insight was radical in its simplicity. He bent these sheets into half-cylinder forms, creating a structure that needed no internal supports, could be assembled directly on the ground, and could be erected rapidly by virtually any soldier, regardless of prior construction experience. In March 1916, at EPRA, Nissen demonstrated the first prototype with a small team of 6 men, using only standard-issue tools, and within 4 hours, a fully functional, weatherproof hut stood ready, shedding rain and artillery fragments with remarkable efficiency. The curved corrugated shell eliminated vertical weak points, the overlapping panels distributed stress evenly, and the simplicity of construction meant the British Army could implement these shelters en masse without diverting skilled labour from other urgent tasks. When Nissen presented the design to Army Command, he promised that any infantryman, following minimal instructions, could build a hut in 3 days, and all materials could fit on a single lorry. The War Office immediately recognized the potential, conducting field tests at Richborough Port with the 172nd Tunnelling Company, where 20 huts were erected in April 1916. Each hut measured 16 feet wide, covered 600 square feet, and withstood the elements in a way that conventional tents and wooden shacks could not. By June 1916, Nissen huts began appearing across British sectors of the Western Front, and the War Office placed a massive order of 10,000 units to be manufactured and shipped before winter. The genius of the Nissen hut lay not only in speed but in the elimination of complexity. Corrugated steel sheets came pre-drilled, wooden end walls were prefabricated, and foundations were optional, allowing a sergeant and 5 privates to erect a complete, habitable structure capable of housing 30 men comfortably or 50 in emergencies. Ventilation panels and the natural gaps in corrugated steel prevented condensation. The curved roof offered sufficient vertical space for standing, and the overall design allowed assembly even under artillery fire. During the battles of late 1916, Nissen huts provided immediate shelter for wounded soldiers evacuated from the front lines, and by the armistice in 1918, over 100,000 had been deployed across Europe, the Middle East, and Africa, serving as barracks, hospitals, depots, and command posts wherever the army needed rapid infrastructure. Field adaptability was central to the Nissen design. In Mesopotamia, huts were built without wooden end walls, using bricks scavenged from ruined villages. In Egypt, bases were laid directly on sand and interior poles cut from palm trees replaced milled timber. Canadian units at Vimy Ridge in 1917 erected huts during active bombardment in 30-minute shifts, operational within 18 hours and immediately housing 40 wounded soldiers. Logistics were dramatically simplified. A single railway flat car transported materials for 8 huts, including 48 corrugated steel sheets, wooden components, and all necessary hardware. Construction teams maintained unprecedented efficiency, completing huts within 6 hours when working in rotation. The British Army's reliance on Nissen huts underscored the importance of speed, simplicity, and adaptability in wartime engineering, principles that would later influence American military shelter design during World War II. The United States Navy, aware of Nissen's achievements, sent Commander George F. Dorrit to study British temporary construction methods in 1940, assessing whether they could support American military expansion prior to entering the war. Dorrit's report meticulously documented Nissen hut speed, material requirements, and ease of assembly, concluding that while they were the fastest field structures ever designed, American forces would need modifications to suit domestic operational doctrine, which prioritized durability and permanence. Following Pearl Harbor, the Navy Civil Engineering Corps developed the Quonset hut, a structure heavily influenced by Nissen principles but incorporating an internal steel framework, insulation, integrated electrical systems, and wooden floors. This framework-first approach, while enhancing durability and comfort, introduced complexity, weight, and logistical challenges absent from Nissen's minimalistic design. The construction sequence became multi-phased: erect the framework, attach exterior panels, install insulation, line interior walls, integrate electrical systems, and lay floors. Whereas Nissen huts could be assembled in 36 to 54 hours under field conditions, Quonset huts often required 90 to 100 hours for completion, especially in forward combat zones with heat, humidity, uneven terrain, and limited labor. Despite these challenges, the Quonset hut excelled in controlled environments, providing insulated, comfortable, and durable structures suitable for long-term military installations, training bases, and re-echelon facilities. Forward combat units, however, consistently reported Nissen huts' superior speed and adaptability, as they could be erected rapidly on uneven terrain without reliance on specialized components, providing immediate protection for troops under fire. The Pacific Theater exemplified these differences. 1st Marine Division personnel received Quonset huts in 1943, but the extreme heat and humidity made steel framework components too hot to handle, slowing construction dramatically, while Australian forces using Nissen-style huts completed shelters in 36 hours under identical conditions. During rapid expansions, such as at Fafudi Atoll in 1943, emergency operations demonstrated that Nissen hut simplicity allowed armies to provide shelter for thousands of personnel far faster than Quonset huts, which required additional labor and technical precision. The inherent speed of Nissen huts proved decisive in wartime logistics, particularly when rapid deployment and adaptability were paramount. The differences between Nissen and Quonset huts extended beyond construction speed to cost, adaptability, and post-war legacy. A 40 by 20 foot Quonset hut cost approximately $850 in 1943 dollars, whereas a comparable Nissen hut cost roughly $230, reflecting both the increased material, labor, and complexity required for Quonset assemblies. The United States produced approximately 170,000 Quonset huts between 1941 and 1946, a feat of industrial standardization and mass production that required precisely interchangeable components manufactured to tight tolerances. Britain, with far less industrial capacity, produced roughly 100,000 Nissen huts during World War I, prioritizing simplicity, flexibility, and rapid deployment over perfect standardization. Quonset hut steel frameworks allowed upgrades, electrical integration, and interior partitioning, making them suitable for permanent or semi-permanent facilities such as Naval Air Station Alameda and training bases where longevity and habitability were key. Nissen huts, by contrast, remained ephemeral, able to be dismantled and relocated as front lines shifted, with modular panels reusable in multiple theaters, demonstrating a philosophy rooted in immediate operational needs rather than comfort or permanence. The legacy of these designs continued post-war. In the United States, surplus Quonset huts were purchased by civilians for housing, storage, and workshops, some remaining in use for decades. In Britain, Nissen huts were largely dismantled and scrapped, though a few persisted as agricultural shelters in remote locations. Architectural criticism often failed to recognize the functional ingenuity of both designs, deriding Nissen huts as corrugated embarrassments and Quonsets as industrial eyesores, yet both provided effective, economical, and rapid solutions to unprecedented shelter challenges. The contrasting philosophies exemplify a core principle of engineering under constraint. Simplicity, speed, and adaptability often trump technical sophistication when survival and operational effectiveness are at stake. Modern military and emergency construction continues to grapple with the lessons of Nissen and Quonset huts. Rapid deployment shelters, containerized housing, and modular units echo Nissen's emphasis on minimal components and fast assembly, while contemporary permanent bases draw on Quonset principles of comfort, insulation, and durability. In disaster relief, the balance between speed and quality mirrors the choices faced on the battlefields of Europe and the Pacific. Following Hurricane Katrina in 2005, the limitations of complex manufactured housing highlighted the continuing relevance of Nissen-style rapid deployment. Structures requiring minimal labor and simple components could have provided immediate shelter while permanent reconstruction proceeded. Similarly, modern expeditionary advanced base operations adopted by the U.S. Marine Corps in 2019 revisit these principles, prioritizing speed of deployment over long-term comfort, reflecting a direct lineage from Nissen's original question: what is the absolute minimum required to keep personnel safe, dry, and operational? This philosophy, embedded in military logistics and engineering, underscores a fundamental insight. The best solution is not necessarily the most advanced or comfortable, but the one that accomplishes its essential purpose under the constraints of time, materials, labor, and environment. Nissen's corrugated steel huts, erected by a handful of infantrymen in days, saved countless lives and provided a template for rapid shelter that informed global military construction strategies. Quonset huts, while slower and more complex, offered enduring utility and adaptability in peacetime and semi-permanent installations. Together, they reveal the tension between expediency and permanence, speed and comfort, simplicity and sophistication, a lesson that continues to shape architecture, engineering, and disaster response nearly a century later. The survival of Quonset huts in civilian use and the ephemeral but historically critical deployment of Nissen huts serve as enduring testaments to human ingenuity under pressure, illustrating that true engineering success lies not only in technical excellence but in contextually appropriate solutions that prioritize effectiveness over perfection. The historical trajectory of these shelters, from muddy trenches to rural farms, from active battlefields to civilian homes, demonstrates the profound impact of design philosophy on operational outcomes, military logistics, and the human experience of war. They stand as enduring symbols of the power of innovation born of necessity, the transformative effect of practical simplicity, and the often overlooked truth that in both war and life, speed, adaptability, and minimalism can outperform complexity, cost, and elegance when circumstances demand it. The lessons of Nissen and Quonset huts extend to broader applications, from modern military doctrine to disaster response and emergency housing. The tension between speed and comfort, simplicity and sophistication, is as relevant today as it was a century ago. Modern expeditionary base operations, rapid deployment disaster shelters, and even field hospitals reflect the influence of Nissen's philosophy. Minimal components, rapid assembly, adaptability to available materials, and the ability to provide functional protection within hours rather than weeks. Quonset principles inform long-term infrastructure where permanence and habitability matter, highlighting the trade-offs between complexity, comfort, and speed. Ultimately, the story of Nissen and Quonset huts encapsulates a timeless engineering lesson: effectiveness under constraint defines success. Nissen's huts were never intended to be beautiful or luxurious. They were designed to keep soldiers alive and operational, rapidly and efficiently. Quonset huts improved every aspect of comfort and durability, but at the cost of speed and adaptability. The contrast between the two philosophies demonstrates that the ultimate measure of a solution's value is not its elegance, cost, or permanence, but its ability to meet urgent needs under real-world conditions. Across decades, theaters of war, and even into civilian life, these structures stand as enduring monuments to human ingenuity, problem-solving under pressure, and the enduring impact of practical engineering on survival, strategy, and society.